Hi everyone, here for part 2 of thermochemistry. Now I left you with a cryptic statement, right? It doesn't matter the journey, it costs you the same amount. What does that really mean? Well, when going from reactants to products, that's the journey. Irregardless of how you get there, you can go just a single step reaction, a multi-step reaction, it doesn't matter. The thermodynamics is the same, so it costs you the same energy to go from reactants to products, or you get the same energy back from reactants to products. It doesn't matter how you get from A to B. Okay, and that's the kind of the fundamentals of Hess's law, right? Using that piece of kind of information, which defines a state function, you can do some interesting math. Okay, so let's look at it, right? So we're going to learn how to calculate delta H for reactions, okay, in kind of interesting ways. All right, so as I mentioned, Hess's law is a state function, and the fact that it's a state function allows us to do this interesting math. Now, if I'm going to show you a picture, this is the picture. Right. So here it is. Okay. Now, here are two people. Okay. There's the professor. There's the student. This is obviously pre-lawsuit. That's a joke. Right. So they're climbing up a mountain. They have the base camp at 1,200 feet altitude, and they have at the summit they got a tent, right, which is at 4,800 feet altitude. Yeah. So they're going to climb up the mountain. The young, more in shape student just goes straight up the mountain, right? Whereas the less in shape professor takes the windy, easier path, right? Two routes to the same place. Which one had a higher elevation change? Answer, neither. It's the same. It didn't matter how I got from here to here. The direct route or the roundabout route, it costs the same amount of energy. It had the same altitude change, right? So that's literally how Hess's law works. Hess's law works. It doesn't matter how you get from here to here. You can have a direct reaction, or you can do multiple reactions. Okay, the energy associated with this more complex path will be the same as the direct path, and that's Hess's law in a nutshell, right? So that's the concept. So enthalpy is a state function. It doesn't matter how you get there. It takes the same amount of energy. Okay, so how you get there? Reactants to products. It's for, obviously, our analogies for a reaction. Okay, so a nice way to do this is mathematically, right? So I'll show you this mathematically. All right, so we'll do the direct route first, right? So I'm going to draw a quick number line here. All right, so let's get some numbers. 50, 40, 30, 20. Okay, and this is enthalpy. So this is the amount of stored chemical potential energy inside, right? So we go from, let's say, H1 to H2. Okay, so we're going from H1, which is reactants, to H2, which is products, right? Fair enough. It's a direct reaction, yeah. So delta H equals products, H2, minus reactants, H1. Final minus initial, better put a little arrow there, right? Okay, which equals 30 minus 40, which equals minus 10. Okay, remember, that would be an exothermic reaction, right? Minus value. Okay, so hopefully that makes sense. That's your direct route, right? So it went from 40 to 30. What was the difference? Well, it went down by 10 minus 10, right? Okay, all right, now, that's the direct route. Let's do an indirect. So hit the student going straight up the mountain. Now we have the professor doing the roundabout route, right? So same number line. And I'm going to go from the same place to the same place, which we'll see in a second. But I'm going to go in a roundabout route, right? So there's H2. There's H1. And I'm going to do this. Nope, to there, and then to there. Okay, all right. So there's my journey, right? So what's delta H? Delta H equals, obviously, H2 minus H1, final minus initial, right? But let me define where H2 is, right? All right. So H2, if I want to go here, it's 40 plus 10 minus 30 plus 10. Okay, that defines its position in terms of this one. So if I want it, it's 40 plus 10, 1, 2, 3, minus 30 plus 10. That's defined its position in terms of H1, so it's there, right? So that's the final position. And then I'm going to go minus H1, which is 40. Figure all that out, minus 10. It's the same. So there's my roundabout route there, right? It's the same cost in terms of energy, okay? So in each case, delta H was the same, okay? Either direct or roundabout, it's the same. Doesn't matter how I get from A to B, it costs the same amount of energy, okay? All right. Now, let's get into Hess's law of heat summation. So the easiest example of this Hess's law, this use of delta H's, is heat summation. So literally it's very, very simple. You just add them, okay? So if I add reactions, I add delta H's. So let's read this one. So Hess's law of heat summation for a chemical equation that can be written as the sum of two or more reactions or steps. The overall reaction equals the overall combined energy, right? So if we add reactions, we add energy. We add reactions, we add delta H. So here's an interesting one. If I take 2 carbon atoms, or 2 moles of carbon, 1 mole of oxygen and gas, I make CO, 2 moles of CO. CO, as you may know, there's the definition. CO, as you may know, is poisonous, right? So you probably wouldn't want to do this reaction in a lab, yeah? So you didn't want to do this experimentally. So what you could do 2 similar experiments, yeah, and then combine them to find delta H for this one. So if we look at this one here, 2 graphites plus 2 oxygens makes 2 CO2, fair enough. 2 CO2 turns into 2 CO plus O2, right? And then we have these delta H numbers. Now for Hess's law heat summation, just add the reactions and see what happens, right? Don't try and predict what's going to happen, just add them, see what happens, right? So for the easy ones, we just add them, right? So remember, add reactants, add products, right? So 2C plus 2O2 plus 2CO2. This, and this, right? There they are. There's my reactants. Turns into 2CO2 plus 2CO plus O2. Fair enough, right? Because I added equations, I add delta H's, yeah? So let me make sure I get these numbers right. So that's minus 787 plus 566. So minus 787 plus 566 equals minus 221 kilojoules. Okay, so that process there has this delta H. Call it delta H3 maybe, equals minus 221. Remember, anything cancel. Now, here's the trick. Things should cancel to give you that equation you want. You were trying to find delta H for this process, right? You combine these. Do they combine to give you that? If so, fantastic, that's what you want. And then, you have the energy associated with that. Anything cancel? Well, there's an O2 there and then 2 of them there. 2 COs and 2 COs. So 2 Cs, 2 Cs, 1 O. I got rid of 2 to leave 1 rather. 2 COs. There we go. So the answer is minus 221 kilojoules. Okay, so that's an easy one. Add the 2 equations, add delta H's. What you're left with when you add should cancel to give what you want. Just add the numbers up. Okay, so nice and easy. There's the first example of Hess's law of heat summation. Sum of delta H's is basically delta H for the reaction because you added the 2 reactions together. Okay, so that's an easy math rule, right? If you add equations, you add delta H. Now, sometimes it's not as simple as that, and we'll see some where we have to make it work by doing some math tricks, right? So, the rules, however, are simple, right? So here's what we do with delta H's when we manipulate equations. So as we saw above, we added equations, we added delta H's. If we were to subtract equations for some reason, we'd subtract delta H's. You guessed it. If I multiply through by a constant, if I multiply everything through by 2 logs on the fire, twice as much heat, multiply delta H by that number 2. No pun, right? 2 TOO. Reverse reaction. Wait, it's interesting. This is the one that's kind of weird. When you flip a reaction, you turn it around, the sign of delta H changes. So if you do a reverse reaction, so it's exothermic one way, it has to be endothermic the other. So if you flip it, you change the sign of delta H. Okay, that's a bit weird, but it makes sense when you explain it. Okay, so basically, that's what we're going to do. All right, so let's try one. So here's a good one. Now I've got you kind of a little bit of a cheat sheet here, right? On the test, obviously you won't have that. Okay, so there's a procedure, right? This is what I recommend you do, okay? So we have to find delta H for this unknown. So 2 sulfurs, 3 oxygen gas makes 2 SO3. This is actually an important industrial process. This is the first step in the creation of sulfuric acid. You burn sulfur to make sulfur trioxide, right? Then you go on and dissolve it in water. That's another day, right? But for now, we have to find delta H for this process. We have 2 related processes. Now here's the big trick, right? You know you want to get this equation at the end of the day, yeah? So you're going to have at the end of the day 2 sulfurs, 3 O2s, and 2 SO3s, with the sulfur and the oxygen on the reactant side, the SO3 on the product side. So what you want is the correct number and, if you like, identity or formula of reactant and product on the correct side, right? Okay. Now if I scan my equations, I see that I have only sulfur here in both of these equations. Sulfur only appears here, yeah? It's on the correct side, reactant side, but it's not enough of it. So I'm going to have to multiply this one through by 2 in a minute, if that makes sense. I need 2 sulfurs. Only place it appears is here. I'm going to need to multiply that through by 2, and therefore multiply that by 2. Fair enough. Oxygen's there, but oxygen's also here. So oxygen is kind of one we're going to ignore for now because it's not unique, right? I'm looking for unique things. Then, when we look here, SO3 only appears here. Yeah, only appears here. There's 2, there's the correct number, but it's on the wrong side. So I'm going to flip that, reverse the reaction, change the sign. So that gives me 2 things to do. I'm going to multiply this one through by 2. I'm going to flip this over and change the sign of delta H, following the 2 rules from before. Okay, so that's basically what the rules say here. So arrange the reactants and products so the kind of unique ones are on the right side, or the correct side, I should say, with the correct balancing numbers. Multiply out if necessary to get the correct number, and then add the reactions. So the last step is the usual step, add reactions. So the first one, remember, we're going to multiply it through by 2. So we call that equation 1, equation 2. Equation 1 times 2. What do we get? 2 sulfur plus 2 O2 goes to 2 SO2. So I'm multiplying through this one by 2, right? Gas. Delta H equals 2 times minus 297 kilojoules, which equals minus, let me just look at this, 594 kilojoules. Okay, so I did that one. That process is minus 594 kilojoules. Now, equation 2, I've got to flip it around, right? I've got to times by minus 1, if you like, the delta H, right? So I've got to flip it around. When I change the sign, I'm really multiplying by minus 1, right? So I'm going to have 2 SO2. This is now going to be a reactant, right? These 2 plus O2 turns into 2 SO3. All right, don't forget your state symbols. Delta H, do you know what it is? It's going to be minus 198. Minus 19. Let's do minus 1 times plus 198, just to show you the math. Minus 198 kilojoules. All right, fair enough. Now what you got to do, add together, add the reactions, Hess's law of heat summation. We play with them a little bit, we'll now add them, right? I like to do that. So 2 sulfur plus 2 oxygen plus 2 SO2 plus another O2, and kind of just copying them down, right? Turns into 2 SO2 plus 2 SO3. Okay. Now, what cancels? 2 SO2 cancels. 2 SO3, 2S, 1, and 2 makes 3, right? So if I just cancel that and put a 3 there. 2 sulfurs. Let's look at back up here. That's what I want. 3 oxygen. That's what I want. and 2SO3, that's what I want. Okay, so yeah, it works out. Delta H equals minus 594 plus a minus 198, so it's more negative, it's minus 92 kilojoules. Minus 792 kilojoules. All right. Okay. So utilize the math rules to manipulate the equations to give the correct or correct number of unique reactants and products. So look for unique things. I mean, sulfur was only in the first equation on the left. That's what we wanted, but we needed two, right? Okay. So rearrange to get the correct number of unique reactants and products and just add the equations. Okay, add equations, add delta H, and then we multiplied the equation through, we multiplied delta H by 2 as well. We flip the direction, we change the sign of delta H. All right, now this one, this is pretty much the standard of the one you'll see on a test, right? So I've given you the rules now, Yeah, what I want you to do is just, pause me, right? Press the pause button and then try it and then come back and see how I did it. Okay. All right, you're back. Okay, so let's look at it. In my first reaction, I have aluminum on the left, and in my desired reaction, aluminum's on the left, and it's unique, right? So we're good. It's on the correct side, but it's not the right number. So I need 4, I've got 2. I'm just going to multiply this one through by 2 right off the bat, right? And then I see, well, there's aluminum oxide, and that's on the correct side. And also by multiplying it through by 2, I get the correct number. So that kind of reaffirms what happened over here, okay? The manganese products and reactants are down here, yeah? So I've got 3 manganese on the right in what I want, but 1 on the left over here. So that's unique. It's going to be minus 1 to flip it and then multiply by 3. So if you like, I'm multiplying that by minus 3, right? That makes sense. So I'm going to flip it and multiply it through by 3 together, right? Thanks. Those are unique reactants and products. MnO2, well, 3 again, right? So it kind of works the same. Okay. So let's do it, right? So equation 1, multiply it through by 2. Okay. So I'm going to get 4, let's multiply this one through by 2. 4Al solid plus 2 times 3 over 2 is 3. 3O2 gas. Turns into 2Al2O3. Delta H equals 2 times minus 1676 kilojoules, which equals minus 3352 kilojoules. Fair enough. All right. First equation done, right? Okay. Next one, I'm going to flip it and multiply through by 3. So I'm going to have 3MnO2. All right, turns into 3Mn plus 3O2 gas solid. And I'm going to say delta H equals minus 3 times minus 521. Minus times a minus is a plus, plus 1563 kilojoules. All right, now add. 4 aluminum rather, 3O2 plus 3MnO2 turns into 2Al2O3 plus 3Mn plus 3O2 gas. Delta H equals minus 3352 plus a plus, which makes it more plus, 1563. Minus 1789 kilojoules. Okay, let's make sure it cancels. Oh look, some oxygens go, and I'm left with, if I can hopefully squeeze them both on at the same time, yeah. 4 alumina, 3 MnO2, 2, 3, 1789. Okay, hopefully you got 1789. If you did, awesome. Okay, if you didn't, all right, just practice, right? It's just relatively simple once you know the rules. Okay, it's all about applying the rules correctly. Okay, all right. Now, there's a funny picture, right? ever watch those, National Spelling Bee shows on the TV with all those really stressed out kids? My wife actually came second in that show. That's how much of a nerd she is. Okay. So here's the analogy, right? Here's the analogy. Think of a spelling bee champion. They have a massive vocabulary of words, right? And from that massive vocabulary of words, they can literally create any sentence they like, right? And that's kind of what we're going to do here. So instead of looking at delta H's for certain fragments of sentences, so think of the cat sat as like one equation, right? And then on the mat as another equation. You've got to look for those two little mini sentences and their heats to add them together to get the cat sat on the mat, right? Okay. Now, think about it. That's not how we work, right? We don't work in terms of sentence fragments and fix them together. We have a big vocabulary. We make our own sentences, okay? So that's what standard heats of formation actually are. They're like the individual words in sentences. If we know a lot of words, we can just combine them together to make any sentence we like, right? And I could have made that sentence, Matt sat on the cat, right? I can have any sentence I want if I understand the concept of words over little mini sentences, okay? And that's what we're going to do. That's what we're going to do. Okay. So that's kind of what I said there, right? Okay. Now, in order to do this, we need to have our vocabulary set up, okay? And our vocabulary is what's called standard heats. Enthalpy is heat, right? Heats of formation, delta HF. And, this is our, say I want water, right? The standard heat of formation of water is defined as the energy associated with making 1 mole of what I want from its elements in their standard states. Okay, so what would the elements be combined to make water? Well, it's hydrogen and oxygen, right? So I need hydrogen and oxygen to make water, but I need 1 mole of water. Right? If I want 1 mole of water, well, it's 1 mole of H2 because there's 2 H's in there, but it's half a mole of O2. So be careful there, right? Standard state. What would it be at room temperature and pressure? Oxygen, right? It's oxygen gas. So for one time and one time only, you can have fractions in equations because the definition is we must have 1 mole at the end, right? Okay, so as long as you've got 1 mole at the end, you can have, for example, half an O2 for 1 mole of oxygen atoms. Okay, so delta HF for that process is this value, okay? If we look in the back of the book, these experiments have been done, right? So if we look in the back of the book, oh, there they are. It's kind of a long way from the camera, all right? Hopefully if you've got the packet in front of you, look to the back, okay? If you notice, a few of them are 0. Carbon in the form of graphite is 0. Chlorine, Cl2 is 0. F2 is 0. Silver metal is 0. Oxygen, O2 is 0. Interesting. Why would some of the heats of formation be 0? If I want to make oxygen gas from its elements in its standard states, I turn oxygen gas into oxygen gas. How much energy does that cost? Nothing, right? So if the product is already in its standard state at room temperature and pressure, it's 0 energy, okay? So that's a little trick. Be careful of that, right? Okay, students always get panicked on the test because they scan the data sheet and they can't find delta HF for oxygen or something, okay? Because it's by definition 0. I'm not going to put it on the data sheet. If you can't find it on the data sheet, there's a reason. It's probably 0, right? Okay. All right. So let's flip over here. Now, there's a couple of ways to think about this, okay? I'll show you the one that really helps with understanding first, and then we'll skip to a formula which everybody uses, okay? To be honest, I don't mind how you do it, but the formula is the standard, right? But you've got to know where the formula comes from, right? So now recall, enthalpy is a state function. Doesn't matter how I get from A to B, the energy is the same, but that's the genesis of this, right? Okay? So what I'm going to do, when I look at an equation like this, okay, if you've ever been in a riot, maybe recently, right? This is CS gas. This is used to disperse crowds, right? So they throw the canister and then the stuff starts spilling out. Yeah, it's actually CS2 liquid, and then it quickly vaporizes, forms CS2 gas. Now think about it. When you have water and you turn it from water to steam, that costs energy, right? So that's called the heat of vaporization. The heat of vaporization is defined as energy needed to turn 1 mole of stuff at its boiling point to a vapor, from a liquid to a vapor. All right, that's called heat of vaporization. So we can actually work out the heat of vaporization of CS2, right? So we have this CS2 liquid turns into CS2 gas. We want to find out that, right? All right. Now, remember, it doesn't matter how I get from A to B. The definition of heat of formation is making 1 mole of stuff from its elements in their standard states. So I'm going to have like a little box down here, right? So here's my little box of Legos, and in there I've got 1 mole of carbon and 2 moles of sulfur, right? Okay. When I take 1 mole of carbon and 2 moles of sulfur and I turn them into CS2 liquid, that is by definition the heat of formation of CS2 liquid. 1 mole of products from its elements in their standard states. Carbon's just solid carbon, sulfur, solid sulfur, just the symbols, right? So that there is heat of formation CS2 liquid. That is delta HFCS2 liquid, which is plus 87.9 kilojoules. So what it's saying is it costs me 87.9 kilojoules to turn this into this. Fair enough. All right. How much does it cost me to make this one? Well, it's going to be the heat of formation of the gas, all right? That's the gas number, plus 117 kilojoules, which is the heat of formation of CS2 gas, right? All right, fair enough. So each one of these steps is the heat of formation, and you can do a heat of formation for anything, right? Okay, every known formula has a heat of formation associated with it, right? Now think about Hess's law for a second. If I want to get from A to B, well, what's my alternate journey, right? It's against this arrow and with this arrow, right? So delta heat of vaporization equals against, right? I'm going in the reverse direction, so it's minus heat of formation of CS2 liquid, so it's against that arrow, right? So it's minus, it's a reverse reaction, right? But I'm going with that one, so it stays the same sign, plus heat of formation CS2 gas, which equals, change the sign, minus 87.9 kilojoules plus 117 kilojoules equals, now think about it for a second. Does it cost energy to turn a liquid into a gas? Yes, it does. So I expect a small positive number, and that's exactly what I get, 29.1 plus 29.1 kilojoules. Fair enough. That's the graphical method. I learned that in high school, and like, it's kept with me to this day, right? Because I like maps, as you may know, right? Okay. So, against, with, if you think about it, that gives me a very, very simple kind of template, right? And this is the genesis of the formula, right? So if you think about it, delta H for the reaction, going from here to here, is minus heat of formation reactants. Because I'm going against, always. I'm always going to go against for reactants. And I'm always going to go with for products, plus delta HF products. Fair enough, right? But we don't like to do the minus and then the plus. We like to do the plus and the minus. And that's why the formula, and that's kind of, you know, with all the bells and whistles, but very simply, the formula is delta H reaction, oh, got 1 minute, equals, put this one first, delta HF products minus delta HF reactant. Okay, that's a perfect place to stop. The generic form of heats of formation. Okay, stop there. Come back in a second. All right, so we saw the very simple generic form, products minus reactants. Always in chemistry, finest minus initial, right? So it's kind of analogous to certain other things we've done, okay? What I want to do is solve this one up here using this basic formula, right? So it's heat of formation products minus heat of formation reactants, right? So the heat of vaporization, I'm going to move to the next page, top of the next page, right? So there's a little blank space where you can do this. So using the formula, that heat vaporization equals, well, let's use the the correct formula here, right? So it's the sum of, meaning if I've got multiple products and multiple reactions, sigma is just sum of. So I just add the individuals, right? But in this one, there's only one of each, so it's kind of easier. We use this term a little bit later. And it's just the prefix for the, the stoichiometric constant. It's one of each, right? So it couldn't be any simpler. Both of these are one, right? Okay. So it's heat formation products. If we look up here, the product, actually, let's write it down. Delta H formation product minus reactant. Okay. We look at our little diagram up here. Let me bring this down so we can see. Magic of paper, right? Okay. So there's our reaction. That's product. That's reactant. So product, the gas one, that's that one. So it's going to be plus 117 kilojoules, okay? And there's only one of them, right? So if you like, there's a 1 in front. Product minus reactant. So, maybe do that, okay? 87.9 kilojoules. 117 minus 87 equals, same as we had before, plus 29.1. Just put plus 29 kilojoules. Okay. All right. So it works just the same. Okay. It's just, if I use my analogy from before, this is directions. This is a map. You never get lost with a map, but to be honest, the directions are simple. So, this is why people generally default to this one, right? Okay. Now, what I want you to do, since we're probably going to go forward using the formula, okay, try and solve this one using the formula, right? So we're going to work out the heat of vaporization of water. So 1 mole of H2O liquid, this is how much energy you got to put into water at 100 degrees C to turn it into steam at 100 degrees C, right? 1 H2O gas. Exactly the same process as before. All right, try that. Okay. All right, let's do it. So, products. Well, let's just write delta H formation H2O gas, right? So it's products first minus heat of formation H2O liquid, which equals, there are the numbers. There's the gas, minus 241.8 kilojoules, minus, now be careful, this is why I like brackets, right? Minus 288, oh, sorry, yep, reactants 285.8 kilojoules. All right, so it's a minus and that's going to be a plus, it's going to be a slight positive. Hopefully you got 44 kilojoules. Okay. Oh, give it up. 44 kilojoules. Now, if I vaporize 2 moles of water, what would I get? Twice as many things, twice as much energy, right? So if I did this for 2, yeah, I just put a 2 in front and a 2 in front and I'd get 88, yeah? We'll see that again in the next example. But simply, if I have 2 moles here and 2 moles here, I put 2 and 2, and I get 88 kilojoules. Okay. All right. That's an extensive property. Twice as much stuff, twice as much heat. All right. Now this next one says harder worked example, right? Harder worked example. Yeah, this is a true test, right? So if you can do this one, I'm super impressed. Try it by yourself, right? So we got numbers in front, and then we got multiple reactants, multiple products. So it's going to be 4 of these heats of formation, 5 of those heats of formation, 4 of those heats of formation, 6 of those, right? Okay. So just think generally, products minus reactants, right? Okay. So what is delta H reaction? Yeah, we write it at the back usually, right? Okay. Now again, some of the numbers aren't there because that's 0 by definition, right? That's 0 by definition. Okay, give it a shot. The answer is not given, and then come back and see what I get. All right. Okay, so I'll do it graphically just for fun, and I'll do it formula, right? So graphically, real quick, let's just do that. So 4NH3 plus 5O2 turns into 4NO plus 6H2O, right? Okay. Now think about it. What do I have to have in my box of elements to make these things? Well, if I look here, I've got 4 ammonia, right? So that's 4 nitrogens. So that's 2N2. That's this elemental form of nitrogen standard conditions, right? 4 3s are 12. So hydrogen goes in 2. So that's 6H2, right? And then oxygen is already in a standard state trig, right? All right. So if you like, that's my box of Legos, yeah? And that is going to be that one. 4 times the heat of formation of ammonia. That one's going to be 5 times the heat of formation of oxygen gas, which is 0, right? That's going to be 4 times the heat of formation NO, and that's going to be 6 times heat of formation of steam, H2O. All right, right? So in words, delta H reaction equals, it's going to be minus, right? So it's going to be minus 4 times heat of formation of ammonia. This is why it's a pain in the neck with signs. All right. If I like, I'm going to put it, right? So I'll put these guys in a square bracket, right? And I'm going to add 5 times the heat of formation of oxygen gas. It's not on the list because it's 0, right? Okay, so that's those. Oh, I'm adding a minus. I'm going against. So there we go. Careful, right? And then I'm going to go up here, right? Plus 4 times the heat of formation of NO plus 90 plus 6 waters, or steams, minus 241. That's a mouthful. Work all that out. You'll get minus 906 kilojoules. All right. Okay. Yeah, it's easy to use the formula. Let's do the formula. All right. So let's just look at the formula. Right. So it's the sum of the number of moles delta H for products minus the sum of the number of moles delta HF reactants. All right. So sum of products. 4 of these, so N would be 4, and it's the sum of, I'm going to add it to 6. Oh. Sum of these two, right? N is 4 and 6 respectively, so it's going to be 4 times the NO number plus 90.3. All right. Sum of plus 6 times the water number 241 minus. Okay. Minus 4. You see how the signs kind of work themselves. Oh, sorry. There you go. It's difficult to get them both on the sheet here. Oh, there we go. Okay. So 4 NO2s, 6 steams, all right? Minus, because that's the thing there. This is the sum of, so let me do it. Sum of this and this, right? Number 4 and 5. So 4 times this number plus, because it's sum of, 6. Oh, sorry, let me start that again. Did it backwards, right? 4 products times this number plus 6 times this number. Products minus reactants. 4 NH3s. NH3 is minus 45. Sum of 5 O2s, 5 zeros, equals minus 906. Okay. Nope. A little clunky there, but hopefully you cottoned on there. So, highly recommend this, okay, if you understand, right? So the sum of the products heats of formation, taking into account the numbers of each type of product, right? So 4 of these plus 6 of these. That's what we got, right? That's what we got down here. And then products minus reactants, 4 of these and 5 of those. But I'm subtracting, so I don't have all that problem with the sign. I just put a bunch of brackets around it, and it makes more sense. Okay. Now, if you didn't get 906, negative 906 for that one, run it again, okay? And just be very kind of careful as you put things into the formula. Brackets are your friend, right? So this is the product square brackets with the products inside. This is the reactant square brackets with the reactants inside. Products minus reactants. Okay. Last but not least, here's a final one. The answer's given, right? So, without peeking at the answer, no, don't look at that. Try work it out, right? Try work it out. I'll give it a shot, all right? I'll give it a shot. So, let me use the formula method. So I'm going to write it out as my simple, this is how I like to do it, when I do it just for me. Heat of reaction is products minus reactants, delta heats of formation, right? Okay. So when I look at that up here, products, right? So it's going to be, if I put it kind of into a pseudo formula, 2 times the heat of formation of SO2, 2 of them, right? 2 of these, plus, because it's sum of, right? 2 times the heat of formation PBO, square bracket. So that's that term done, right? Minus 2 PBS plus, because it's the sum of, right, 3 heat of formation O2. Just about enough room. Okay, so I just stick old numbers in, right? So that's 2 times SO2 minus 296.8. I'll put the kilojoules in at the end, right? Plus 2 times PBO minus 219 minus 2 times PBS plus 3 times 0. It's not there, right, because oxygen's in its standard state. Run that through, what you get, minus 835.6 kilojoules. Okay. That in a nutshell, if you followed that through from start to finish and you understood it and you got the same answer, you're in good shape. Okay. All right. Stop there. A couple of interesting things in the appendix. Not too much, really, but take a look. All right. See you guys next time.